Good day to all attendees. My name is Maximiliano Rios Vargas. Today I will present our work titled Green Synthesis and Characterization of Zinc Oxides decorated with different gold compositions for use as electrocatalysts for alcohol oxidation. This project addresses two interconnected challenges: the development of efficient and sustainable catalysts for direct alcohol fuel cells and the valorization of invasive marine biomass, specifically Sargassum natans 1. Direct alcohol fuel cells are promising energy conversion devices because of their high energy density, mild operating conditions, and compatibility with renewable low-cost fuels. Among these, crude glycerol is particularly attractive as it is an abundant and inexpensive byproduct of biodiesel production, has a high hydrogen content, low toxicity, and can be converted into value-added chemicals through electrooxidation. The main challenges are its complex molecular structure, which slows oxidation kinetics, and the presence of impurities that can poison the catalyst surface. These issues require highly active and stable anode catalysts. Defect engineering in metal oxides is a proven approach to enhance electrocatalytic performance by increasing surface activity, electrical conductivity, and charge transfer kinetics. Zinc oxide is especially appealing because of its abundance, stability, semiconducting properties, and oxophilic nature, which promotes strong interactions with hydroxyl species. In this work, we employed a green synthesis route using Sargassum natans 1 extract to introduce structural defects into zinc oxide, followed by decoration with gold nanoparticles at different concentrations, aiming to create metal semiconductor interfaces that synergistically enhance glycerol oxidation in alkaline medium. The methodology was divided into three stages. Stage A: green synthesis of zinc oxide nanostructures. An aqueous extract of Sargassum natans 1 served as both reducing and stabilizing agent. Its rich composition in polyphenols and other reducing molecules facilitated the nucleation of zinc oxide nanostructures, while creating oxygen vacancies and other lattice defects known to increase the density of active sites and improve electron transfer. The zinc oxide powders were then calcined to enhance crystallinity while retaining defects. Stage B: gold decoration of zinc oxide. The calcined nanostructures were impregnated with aqueous solutions of gold salt at 5, 10, and 20 millimolar. Reduction under controlled conditions anchored the gold nanoparticles onto the defect-rich zinc oxide. Varying the gold content allowed assessment of the trade-off between surface area, particle dispersion, and catalytic performance. Lower loadings favored fine, well-distributed particles. Higher loadings risk agglomeration and site blockage. Stage C: electrode preparation and electrochemical evaluation. The zinc oxide gold nanocomposites were dispersed and drop cast onto glassy carbon electrodes. Tests were performed in 1 molar potassium hydroxide with varying crude glycerol concentrations. Results and discussion. Structural characterization. X-ray diffraction confirmed the hexagonal wet side phase of zinc oxide in all samples with no secondary phases. Metallic gold peaks became more intense as loading increased, confirming deposition without altering the zinc oxide lattice. Morphological analysis. Scanning electron microscopy showed granular zinc oxide with high surface roughness. At 5 and 10 millimolar gold, nanoparticles were well dispersed, creating numerous metal semiconductor junctions. At 20 millimolar, larger agglomerates formed, potentially blocking active sites, despite increasing the total electrochemically active surface area. Ultraviolet visible spectra revealed the gold surface plasmon resonance band in decorated samples, absent in pure zinc oxide. Band intensity grew with gold content, indicating more nanoparticles on the surface. Electrochemical performance. Electrochemically active surface area increased with gold content, but higher values did not guarantee better activity. The highest specific activity, normalized by gold loading, was obtained for zinc oxide gold 10 millimolar on carbon at 27.9 milliamperes per square centimeter of gold. This is comparable to the best gold-based glycerol oxidation catalyst reported. Zinc oxide gold 5 millimolar showed moderate activity, while 20 millimolar, despite the largest surface area, was less active due to agglomeration, reducing site quality and accessibility. Mechanistic interpretation. The proposed bifunctional mechanism involves zinc oxide absorbing hydroxide ions from the alkaline electrolyte and transferring them to nearby gold sites where glycerol oxidation proceeds more efficiently. The optimal balance of gold dispersion and zinc oxide gold interface in the 10 millimolar sample explains its superior performance. Conclusions. We successfully synthesized zinc oxide gold on carbon catalyst via a green route using Sargassum natans 1 extract, producing defect-rich zinc oxide that anchored gold nanoparticles effectively. The zinc oxide gold 10 millimolar composition exhibited the highest specific activity and the most favorable onset potential for crude glycerol electrooxidation in alkaline medium. The results showed that noble metal loading and performance are not linearly related. Optimal activity depends on balancing surface area with strong metal semiconductor synergy. This work not only advances electrocatalyst design, but also demonstrates the value of converting invasive biomass into high-performance materials, addressing environmental and energy challenges simultaneously. That concludes my presentation. Thank you for your attention.